Hey, it's Miss Murphy. Today I'm going to do a quick discussion on gravimetric analysis, okay? So let me share my screen here. And I'm going to share with this. I'm going to go like this. Share screen with Zoom, okay? And what we're going to do is first go to my notes page here, okay? So we're going to briefly discuss gravimetric analysis. And it's just a fancy word for using gravity to filter something, kind of, all right? So imagine that you have a couple of background pieces of information that you must know for this course. Is something about our solubility, right? Soluble in water. You do not need to know your solubility rules, all of them, right? Which is good. You don't have to memorize them, but you have to know. You must know that nitrates, ammonium, I'm trying to think of what else you have to know. Group 1A. Oops, that's a group 1A. All right, I'm going to fix that. It does not look like a 1A. Group 1A, your alkali metal compounds. All of these are soluble, always. All right? That means when you put them in water, they will dissolve, okay? Very important to realize. Nitrates, ammonium, group 1A compounds are always soluble. Now, it's also important, let's see, let me, Ms. Murphy, focus here, stay on task. When we perform a gravimetric analysis problem or lab, we would take a compound that is soluble, typically, okay? And we would add it to another compound. Let's see, let's do VY, that is soluble, all right? And we would form, typically, let's see, XW, another compound that is itself soluble, and another compound that is insoluble, right? So we call that insoluble compound our precipitate, right? We envision that we have our solution, our mixture, and we have initially we've got X ions and Y ions and V ions and W ions, whatever they are. And we see that V and Y, these two ions, form an insoluble salt, okay? So that insoluble salt forms at the bottom of our solution. And what we have going on in here, oh, I don't want that, I just want a different color. What we have going on in here are some of our X ions, some of our W ions. Now, I am concerned with, let's say that I'm concerned with W, all right? And this, right, this yellow is, that's not W, that's Y. This yellow will say, is that solid, right? And for my analysis purposes, I'm concerned about letter Y, okay? What that means is when I combine, my concern is with Y, and my goal is to precipitate all of the Y ions. Well, that means that I have to add enough of this V ion containing compound, the compound that contains the V ion. I must add enough of it to ensure that all of the Y ion is precipitated. Therefore, I must add this solution in excess to ensure that all of the Y ion is precipitated and ends up into the precipitate. All right? Otherwise, this process doesn't work. And you need to be able to explain why this needs to be in excess to ensure that all of the Y ion precipitated. Okay? We could then filter this solution this one right here, right? This solution right here would get filtered. We would then rinse the solution. Why are we going to rinse these? Oops, it's not a solution anymore. We would then rinse the precipitate to ensure, oh my goodness, what happened there? To ensure that it's pure and essentially to wash off any remaining ions. So you could envision that some of the X and Y ions might be attached to our precipitate. So we need to rinse it to ensure that those are gone and that our precipitate is pure. By pure, it is purely VY solid and nothing else. Once we filter it and rinse it, we will dry until we have a constant mass. Let's say until mass is constant. So we would dry it, weigh it, dry it, weigh it, and we would continue to do that until the mass stops changing, and that is to ensure that all the water is removed. Oh my goodness, sorry. Okay, so in this type of problem for AP Chem, right, is typically used when we have an impure sample and we use this approach. Let's say that this here came from a sample that was impure. An impure sample, it contains more than one substances mixed together. Well, what we would do is precipitate part of one of the substances, isolate the precipitate. We would have to eventually, let me go back down here. We would eventually have to get the mass of that precipitate. Oh, we've already done that. We got the mass. And we could then do some math to determine the percent purity of the original compounds. Okay, so let's look at a practice problem that Ms. Murphy has pulled up right here for you. There's actually two practice problems. Let me get myself out of the way. And you'll see that the practice problem pretty much goes through what I just went through. And we'll look at number 1, okay? So a 2.00 gram sample of limestone. Limestone is impure, but it contains a lot of, oh my goodness, stop. It contains a lot of calcium. Well, the limestone is dissolved in hydrochloric acid. That means it ionizes, right? When it dissolves, it turns into ions, and it produced the calcium ion. So we know that some of the calcium ion is a component of limestone. All right. We then took that calcium ion and we added this to it. Notice this is soluble. Ammonium compounds are soluble. So what we had was calcium ions. We added our dissolved, this was dissolved, it's aqueous. We added this, and it was the oxalate ion. And what happened was the calcium ion met the oxalate ion and formed the precipitate calcium oxalate. That's an S for solid. And we would imagine that the ammonium ion was still floating, ions were still floating around in the solution. Okay, so we cross those off. And what we see is the calcium, because of the oxalate, it had formed a precipitate. It precipitated out of the solution. So we end up with a net ionic equation as such. Okay. Now we know that the calcium oxalate that was then filtered, they did not include the word rinsed, but they need to, and then dried and weighed to a constant mass, turned into a mass of 2.43 grams. All right, the question is, determine the percentage by mass of calcium in the limestone. Well, I know that the original limestone had a mass of 2 grams. The question is, what percent of that was actually the calcium? Okay, so this is pretty easy here, guys. Let's take the 2.43 grams of the calcium oxalate. Let's calculate the molar mass. I'll do that real quick. I should have had it already. I apologize. 40.01 plus 24.02 plus 16 times 4 is 128.03 grams for every 1 mole. What is that moles of? That's moles of calcium oxalate. We see that every 1 mole of the calcium oxalate contains 1 mole of calcium ions. Well, that's exactly what we're talking about. Determine the percent of calcium in the limestone. So since it gave me a mass of limestone, let's turn these into grams, right? Let's turn the moles of calcium ions into grams of calcium ions. All right, let's do the math there. 2.43 times 40.01 equals, divided by 128.03 equals, that gives me 0.759. I could keep another sig fig if I wanted. It's not going to change anything. Grams of calcium that was precipitated into this precipitate that is in the solid that precipitated. Question is, determine the percent by mass of calcium in the limestone. Well, that means there's this much calcium here in our 2-gram sample of the limestone. So if we just divide that, we can get our percentage, 9.4 grams of the calcium in every 2.00 grams of limestone. Leads us to conclude that the percent of calcium in the limestone is 38.0% calcium ion. All right. Okay. Let's clean that up. And the next problem is extremely similar. But since it's there, I'm going to go ahead and do it with you. Okay. Let's see how well that works. I wish I had a bigger eraser. Okay, so next problem, let's figure out what's going on here. We have a simple sample of impure potassium chloride. Impure, it's not pure, something else is in there. We dissolved the potassium chloride in water, which gives us the potassium ion and the chloride ion. Remember, anything group 1A dissociates. If you don't recall, when an ionic compound dissolves in water, it dissociates into its ions. So what we have when we dissolve in water is we have these two ions here, okay? And it's treated with an excess of silver nitrate, okay? And the silver nitrate, now I want you to realize, remember, silver nitrate, I'm gonna have to erase this, was put into solution. So that gave us the silver ion in the solution and the nitrate ion in the solution, okay? So what we have are these 4 ions floating around in our solution. Well, group 1A metals, such as potassium, are always soluble, so he will not precipitate out. Nitrates are always soluble, so he will not precipitate out. But what happened was the silver chloride precipitated out because it is an insoluble compound. It does not dissolve in water. So by treating the potassium chloride solution with the silver nitrate solution, we caused a precipitate of silver chloride to be produced. I hope that you see why it was so important that this be in excess. All right, because we had to ensure that all the chloride was precipitated out. What would be in our solution, right? If we make our silver chloride this, what ions will be that's silver, what ions will be floating around in the solution? These are questions that you should be able to answer, okay? Well, we would expect to see several different ions. We would definitely have some potassium ions in here, right? Because they did not participate, they're still floating around. We would not have any chloride ions because the potassium chloride was not in excess, it all precipitated. We would have silver ions because the silver nitrate was added in excess. Therefore, all of the silver did not precipitate. We would also have nitrate ions because the nitrate was a spectator ion and did not participate. All right, so I hope you understand what I'm talking about. And if you don't, you at this point need to stop and write down your question so that you can bring it to me, okay? Now, the problem tells us that after we did all that, we isolated our precipitate, we filtered it, we rinsed it, and we dried it, all right, until we had a constant mass to ensure that all of the water was gone. We have a precipitate that has been washed, filtered, rinsed, and dried several times. That weighs this right here. That's kind of messy. And there we are. And the question is, calculate the percent KCl in the original sample. Well, the point is that all of this came from the KCl. So however much chloride is in here can lead us to how much chloride was in here can lead us to more information about this compound. So same process that we took 8,402 grams of AgCl, 143, if I'm right. Yeah, this is like 143.5 0.34 grams of AgCl in every 1 mole of AgCl. We know I write everything because y'all are learning from me. We know that 1 mole of AgCl has 1 mole of chloride. I also see that the compound that the chloride came from contained 1 mole of chloride. If it was a Cl2, I would put a 2 there for every 1 mole of KCl. And then what I will need to do is convert my moles of potassium chloride to grams of potassium chloride using the molar mass. And that's grams of potassium chloride. Okay, so let's do the math. 0.8402 times 74.55 equals, divided by 143.34 equals, and that tells us that in our original impure sample of potassium chloride, it contained 0.437 grams of potassium chloride. And we figured that out through the process of gravimetric analysis. Now, the percent of this would be the potassium chloride divided by the mass. Oh, guys, I lost my significant figures right here. I see this is 4, this is 4. I should have 4, and I still have it in my calculator. So I'm going to write 0.43670. Actually, I won't round it all. I'll just keep more and round when I'm done. All right. And then multiply by 100. So that's still in my calculator. I'm just going to divide it by 0.45 times 100. And that gives me 97.1% KCl in the impure sample. All right. And that's about that. So that's how you're going to do the gravimetric analysis, and pretty simple. Okay, talk to you later. Bye.